Okay, I want to do exactly the same thing that we did in the previous problem, only this time with a different function. X to the fourth minus 8x squared plus 16. So once again, we're going to find the largest open intervals upon which f is increasing and decreasing. Once again, we're going to find and classify all critical points as either relative max, relative min, or neither. We'll find open intervals upon which f is concave up and concave down. We'll find all points of inflection. We will find all x and y intercepts. And then we'll sketch a good graph of the function, a good careful graph of the function. Once again, parts A and B have to do with the first derivative, where it's positive, where it's negative, where it's zero. C and D have to do with the second derivative. This is pre-calculus, and here we put it all together. So let's start as we did last time by taking the first derivative and doing a sign chart for it. So an advantage, of course, of doing this by video is you can pause it at any time. If you want to get ahead of me and go ahead and take that derivative and do the sign chart and then just check your answer, please feel free to do so. But I'm going to go ahead right now. Derivative of x to the fourth is 4x cubed. Derivative of minus 8x squared is going to be minus 16x. And of course, that goes away. If we set f prime of x equal to 0, we have 4x cubed minus 16x is equal to 0. We can certainly divide both sides by 4. So x cubed minus 4x is equal to 0. And then we can factor out the x. We could have done that all in one step. So x times x squared minus 4 equals 0. This thing certainly factors nicely. It factors as x minus 2 times x plus 2. So this thing is 0 at x equals 0, at x equals 2, and at x equals minus 2. Those are the three places where the first derivative equals 0. And I can go ahead and draw a sign chart. So this is a sign chart for f prime. It's 0 at negative 2, it's 0 at 0, and it's 0 at 2. And I can go ahead and plug values in. If I plug, say, a point to the left of minus 2, let's say minus 3, f prime of minus 3 is going to be 4 times minus 3 cubed minus 16 times minus 3. Minus 3 cubed is negative 27, times 4 is negative 108, plus 48, which is what, negative 60? Certainly negative. So it's negative everywhere over here. Now I could plug in 3 more points. I'm going to speed things up. We saw from the last example that every time we hit a 0 does not necessarily mean that the sign changes, but this time it does. So it's positive in here, it's negative in here, and it's positive in here. And again, to get these numbers, just pick any point between minus 2 and 0. I probably would have picked minus 1 and plug it in to see that you got a positive number, and any point in here and any point to the right of 2. And since this is a first derivative, we can go ahead and put our up and down arrows here. By the way, as far as A and B, you can pretty much answer the question right now. You can see where this thing is increasing and where it's decreasing, where it's going uphill to the right and where it's going downhill to the right. You should also be able to tell just by looking at this thing that I have 1, 2, 3 critical points, and which ones are at the tops of hills and which ones are at the bottoms of valleys. The arrows basically give you a skeleton of the shape of the curve, at least the up and down part. Let's go on to the second derivative, assuming we have room. So f double prime of 0, we're going to take the second derivative. The 3 comes down and multiplies the 4. That gives you a 12x squared minus 16. And we can set that equal to 0. So 12x squared minus 16 equals 0. I think I'll divide both sides by 4. In fact, I think I'll divide both sides by 12. So we have x squared minus 16 over 12 is equal to 0. In other words, x squared minus 4/3 is equal to 0. You can do whatever you want with that. I think I'm just going to move the 4/3 onto the other side. X squared equals 4/3. So x equals plus or minus root 4/3, which is the same thing as plus or minus 2 over root 3. That number, if you're looking to figure out where it is on the sign chart, that's about approximately equal to 1.15, plus or minus 1.15. Put the plus or minus in there. Thereabouts. So let's go ahead and do a sign chart for the second derivative. So minus 3, minus 2, minus 1, 0, 1, 2, 3. I was forced to make this small just because I have a small blackboard. So root 4/3, or 2 over root 3, or about 1.15, that's somewhere a little bit to the right of 1. So right there is 2 over root 3, or 1.15, or whatever you want to call it. And that is one place where the second derivative equals 0. It's not at 1, it's right there. And another place where the second derivative equals 0 is negative 2 over root 3. So about there. And again, I'm sorry, things are a little bit crowded there, but I have a small blackboard, best I can do. And that breaks the real number line up into 3 parts. We can pick a point in each part and plug it into the second derivative. Sorry, this shouldn't say f double prime of 0. This should say f double prime of x. Sorry about that. F double prime of x. Then we set that equal to 0. So let's plug a point to the left of negative 2 over root 3 in there. How about negative 2? So that is going to be f double prime of negative 2 is 12 times negative 2 squared minus 16. That's 12 times 4, which is 48, minus 16 is 32. That's positive. And again, I'm going to speed things up. If you plug 0 in, you can definitely see that you get 12 times 0 minus 16. That's definitely negative. So it's negative in here. And if you plug 2 in, you'll find you get exactly the same thing as if you plugged minus 2 in. It's positive over here. And again, this is a second derivative sign chart. It is not a first derivative sign chart. And so, since it's a second derivative sign chart, you don't use up and down arrows here. You use concave up and concave down symbols. Let's go ahead and answer parts A, B, C, and D now, since I think we've done most of the algebra and I have a little bit of room. By the way, when you're doing a question like this, feel free to use lots of room on your page. And remember that the solution is getting quite long now. So please remember that it's not just rough work and then answer. What you should be doing is sort of leading your reader through to the answer. Feel free to use plenty of words. So the answer to A. Find the largest open intervals upon which f is increasing and decreasing. Well, it's definitely increasing, where we see the up arrows here from -2 to 0 and then to the right of 2. I said open intervals right in the problem, so I'll use open intervals. And it's decreasing where we see the down arrows. From -infinity to -2. Oops, I think I want that to be a comma. And also from 0 to 2. I think I'd prefer you had commas there rather than union symbols, since we can't really say it's increasing on that whole set. But be that as it may, I'm just going to ask you to use commas here. Find and classify as relative max, relative min, or neither. All critical points. We have 3 critical points, one at -2, one at 0, and one at 2. So at x equals -2, at x equals 0, and at x equals 2. X equals -2, you can see we were coming down, and then we go back up. This must be at the bottom. This is a relative min. X equals 0, you can see we were going up and then coming down. That must be a relative max. And at 2 again, that must be a relative min. I could just as easily get the y values there by plugging in those 3x values. That would tell me what the y values are, and I will do that when we start graphing. For C and D, find open intervals upon which f is concave up and concave down. Now we're looking at the second derivative sign chart. So concave up from -infinity all the way up to -2/√3. And also from 2/√3 to infinity. Again, I'm going to ask you to use a comma. Concave down from -2/√3 to 2/√3. All the information from C and D can be read right off the second derivative sign chart. D, find all points of inflection. We're looking for places where the derivative exists, which it does everywhere. And the concavity changes. Well, the concavity changes. It goes from plus to minus here. It goes from minus to plus here. It goes from concave up to concave down, and then it switches again. So we have points of inflection at x equals -2/√3 and x equals 2/√3. And again, if you want the y values there, and we will need the y values there when we start graphing, you can just go ahead and plug those x values in. But those are our 2 points of inflection. E, find all our x and y intercepts. So for our y-intercept, there's only going to be one of those. Set x equal to 0. So y equals f of 0. Again, now we're plugging back into the original equation. So 0 to the 4th minus 8 times 0 squared plus 16. Here we are at height 16. So we have a y-intercept at height 16. Y equals 16. And let's go ahead, and find our x-intercepts. We will this time set y equal to 0. So we have x to the fourth minus 8x squared plus 16 equals 0. Now we have to fall back on our algebra skills. If you take a look at this, you'll see that it factors. X squared minus 4 times x squared minus 4. This is a perfect square. It factors just like that. So x squared minus 4 equals 0, or x squared minus 4 equals 0. So x squared minus 4 equals 0. And if that factors nicely as x minus 2 times x plus 2. So x is equal to minus 2, or 2. So we have two x-intercepts, and of course, one y-intercept. We found our points of inflection. We found where the curve is concave up and concave down. You don't have to put boxes around things, but here we go. We have all our answers there, except for our picture. Let me go ahead and try to line everything up as best I can. So our y-axis goes right below the 0. On our x-axis, I will do my best to line everything up. This may look a little distorted on your picture because the camera isn't quite square to the board. But hopefully it looks approximately right. I'm also going to put these points that I've marked down, the minus 2 over root 3 and the 2 over root 3. And let's see, what do I know so far? I know this thing crosses the x-axis at minus 2, and I know it crosses at 2. I know it crosses the y-axis at 16. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Crosses the y-axis right there. Let's look and see what other important points are on this picture. I know I already have relative maxima at x equals minus 2, and x equals 0, and x equals 2. I already know the heights of those points. I have points of inflection at 2 over the square root of 3 and minus 2 over the square root of 3. So let me figure out what the y values are there. Let me plug in 2 over the square root of 3. So again, I'm going to plug it into the original curve. F of 2 over root 3 is 2 over root 3 to the 4th power minus 8 times 2 over root 3 squared plus 16. So let's see, this is going to be 16 over 9. So 2 to the 4th is 16. Root 3 to the 4th is the same as 3 squared, so 16 over 9 minus 8 times what I have here is 4 over 9. Sorry, 4 over 3, I should say, plus 16. And I guess we're going to have to go ahead and get a common denominator there. So that's going to be 16 over 9 minus 8 times, let's see, I'll have to put that over 9 as well. So 8 times 12 is 96. And if I multiply 16 by 9, I get 144 over 9. So let's see, 16 minus 96 is negative 80, plus 144 is 64. So this is 64 over 9. Feel free to do this on your calculator. You don't have to muddle along with the fractions. But 64 over 9 is just a little bit bigger than 7. That's 7 in the 7th. So 64 over 9 is just going to be a little bit bigger than 7. So 1, 2, 3, 4, 5, 6, 7. So at x equals minus root 2 over 3, I'm a little bit bigger than 7 there, and I'm a little bit bigger than 7 here. So those points are, that point is minus 2 over root 3, comma, 64 over 9. And this one is 2 over root 3, 64 over 9. Okay. So we have all the y values of all the important points marked on our page. Now it's a matter of taking all this information from the first and the second derivative, just as we did in the previous example, and synthesizing it into one picture. Again, we'll start from negative infinity. We'll start all the way on the left, and we will move from left to right, and we'll stop every time something changes. So the first time something changes is at minus 2. We go from being decreasing to increasing. So up to that point, negative infinity, all the way up to negative 2, we are decreasing in a valley. So we are decreasing concave up. We flatten out at x equals minus 2. So decreasing in a valley, flatten out at x equals minus 2. It looks like this. Decreasing in a valley, flatten out right there. It gets horizontal. The next time something changes is at minus 2 over root 3. From negative 2 all the way up to minus 2 over root 3, we are increasing, still in a valley. So increasing in a valley. So this thing should still be shaped like a valley, not a hill. It's increasing. From minus 2 over root 3 to 0, we are still increasing. These are still plus signs. We're still going uphill. But this time, we're concave up, so increasing on a hill. And we flatten out at x equals 0. There should be a nice smooth curve. We know that polynomials give us nice smooth curves. From 0 to 2 over root 3, we are decreasing, still on a hill. So decreasing concave down, decreasing on a hill. Make this nice and smooth. From 2 over root 3 to 2, we are still decreasing. But this time, once we pass this point, it is concave up. These are plus signs now. And we flatten out there. We can see that the first derivative is 0 there. Decreasing in a valley. And after that point, we are going up to the right in a valley, increasing concave up. And we have this giant W shape. I think if we've gotten this far, we have every right to be proud of ourselves.